Hello and welcome to the Qubit Guy podcast, brought to you by Classiq, the quantum algorithm design company. My name is Yuval, and my guest today is Robert Wille, professor of computer science. Amongst other topics, Robert and I talk about design automation throughout the ages and discuss the analogies between classical design and the quantum world. We hope you enjoyed this episode. Please let us know how we did by emailing hello@classiq.io. That's hello@classiq.io. Hello, Robert, and thanks for joining me today.
Yeah, hello. Nice that you have me.
So, who are you and what do you do?
Yeah, I'm Robert Wille. I'm a professor at the Johannes Kepler University in Austria, and for many years I work in the domain of design automation. First, starting in the design automation for classical circuits and systems, but now also for more than 10 years, almost 15 years, I'm also working towards developing corresponding methods for quantum computing. That's, I guess, why I'm here.
And just for transparency, you are also part of our technical advisory board, and we're very grateful for that. What does design automation mean?
Yeah, it means, well, automating the process of design. And in this particular case, of course, of the design of circuits and systems, but it could be many other things. And the main motivation here literally is that we have to cope with a substantial complexity when we're designing and developing today's systems. I mean, the next smartphone, the next AI solutions, those are systems you cannot create and develop and design manually anymore. You need at some point design automation because you cannot cope with the sheer complexity. Today's systems, they're composed of millions or even billions of transistors or components, and you don't draw the netlist of such a system on a whiteboard anymore. You need automatic methods for synthesis, for compilation, for checking that everything works correctly. And that's what we develop. And the main challenge indeed is how to cope with this enormous complexity.
So is that like Vhdl or Verilog or these kind of languages that they've been developed for a while? So could you give me a little bit more detail about your specific work, what your group is interested in?
Yeah, this is exactly the programming language or hardware description languages like Vhdl are some of the means we're using. And I would say 50% of our work and research, we're still using to develop methods for classical computing, but the other 50% also for emerging technologies, including quantum computing. And since you asked for a precise example, typical scenario is you have designed something, for example, in VHDL, and a particular control system, something which controls a train or an aircraft or something like that, a traffic preemption as a simple example, as a typical example we use in our lectures. And you have developed that in VHDL. And now you might ask yourself, okay, can you deploy that in the sense that would you feel comfortable that this system is now used in practice? Or do you rather would like to have something like a check which makes sure that nothing bad is happening, nothing unintended is happening with the system? And so what you usually do, you have a design, for example, in VHDL, and then you have certain properties, safety guarantees you want to provide, and then redeveloping methods so that you can simply throw your design and certain properties, for example, to be checked into a black box, and then in a push button fashion, this black box determines whether or not your property indeed holds, or whether or not there might be an situation where something bad is happening, the property is failing, something like that. This is one example, usually the verification example. Other examples, the typical thing is synthesis. You write your VHDL code, you hit a button, and then the VHDL code will be synthesized or compiled when you talk about a software system for a particular architecture, for a particular technology, and so on and so forth. And all those tools where you simply throw your design into it, and then it automatically generates netlists or generates proof conditions, stuff like that. This is basically what we're doing.
So the process of doing this for electronic design, netlist and synthesis and verification has been around for many years. How is quantum similar and how is quantum different than these traditional methods?
There are lots of similarities. Indeed, when we look at the history, these tools you just mentioned, they are available not for a couple of years. In fact, we as a community, we are developing them for decades. And it's interesting to see the parallel development of classical computing and quantum computing, because originally in classical computing, electrical engineers built the first computers. And then over time, they evolved so that they suddenly, as I said, recognized, okay, we need automation. They founded an entire domain, computer science or informatics, around that. So at some point, computers were developed by electrical engineers. And then at some point, the community recognized, okay, we need computer scientists. We need people who develop software, who develop automatic methods for that. And it's very interesting that in quantum computing, we kind of see a very similar development, because the first ideas of quantum computing, of course, came from people from theory. Then physicists have built the first quantum computers. And now more and more we recognize that in a similar fashion as we have seen it many decades back for conventional classical computing, we now can see we now also need people who can develop software for quantum computing, who can realize certain applications for quantum computing. So this parallelism is really interesting to see, because on the same side, we can also see the challenges. We have something in the classical computing world, what we call a design gap or verification gap, which means that our ability to properly design something and to exploit the technology we have is limited. So we have in the classical world till today a situation where we actually can develop or realize more powerful machines than we actually can design useful applications and software for. And in quantum computing, it was interesting. In the past years, when I started on quantum computing, there weren't we didn't have these powerful quantum computers so far. We had very prototypical systems, and they are still limited. But now we see this development in the past years. And my feeling is really that we are approaching, as we did in the classical world, we're now approaching in the quantum world some sort of a design gap, that we may very soon reach the situation where we might have more powerful quantum computers than methods and means to actually use them properly or exploit them properly. And this is sort of what we are working on to avoid this design gap, or at least to keep this gap as small as possible.
When people design abstraction languages, whether it's hardware description languages or the parallel in quantum, then sometimes critics come and say, well, when you design an abstraction layer, you lose something. You lose the ability to take advantage of the unique properties of the machine. And today in quantum, various manufacturers have different properties, different architectures. So is it too early to design a abstraction layer for quantum, or too late? Or how is it relative to the time, in your opinion?
Very good. That's a very good question. And I have sort of two different answers to that. On the one hand side, right now, indeed, we are in a situation where we still have to deal and we have to have a close interaction with the physicists who are building the quantum computers. And I consider myself a computer scientist. And in this regard, I like abstractions, because although I have a rough understanding how the physics of quantum computing work, I'm certainly not an expert in quantum physics. And in this regard, I rely on abstractions, because that's the only way how I can exploit my background in computer science in order to tackle the corresponding complexity. And right now, you're absolutely right that we need to be close to the physicists to understand really the concerns, because today's machines are still limited, and we really have to try to respect and to satisfy the physical constraints as best as possible. However, in the long run, if really the physical community is making the quantum computers better and better, more scalable, more reliable, less error prone and stuff like that, I'm pretty sure we need more abstractions. And again, the nice example is when you just check out how development goes. We had this exponential growth in the classical computing power. And right now, if you check out the roadmaps by IBM, Honeywell, and so on and so forth, you see a very similar development. So sooner than later, I assume we're reaching a situation where complexity is increasing rapidly. And then one of the main ways of coping with this complexity is abstractions. In a similar way that today we're not working with transistors anymore in order to realize an application, we will have in quantum computing also a situation where we will use high-level languages and automatic tools and compilers, which might not be that machine specific anymore at certain abstraction levels. And I think it's totally okay and worthwhile to do research on those abstractions already now, so that we are prepared for a situation that complexity will grow so significantly, and for a situation where also we might be able to handle the physical requirements on those lower levels, and we can abstract them on the higher level. So I really believe both is necessary. We need to cope with these physical details today, but we should also prepare ourselves that we can abstract more from it in the future.
On classical computers, all these abstraction layers already exist, right? If I design a web page, I don't need to know how CMOS transistors work. And there are many, many software layers between the web page and what actually runs on the hardware. So that's good. And let's assume that that was also the situation with quantum computers, that you had an abstraction layer. But today, because of coherence issues and errors, a lot of algorithms are written in a hybrid classical quantum way. Is there a special case of this abstraction once you get into hybrid algorithms, or is it just two separate camps and with a little bit of interface between them?
To be honest, I don't really know. I'm not sure how this whole development will lead us eventually. Right now, my understanding, my feeling is really, if you want to realize an application for quantum computing, you need an understanding about quantum computing. The way how we program a quantum computer, how we're going to use it, right now still requires the corresponding designer to understand how quantum computing works in principle, not physically, but at least methodologically, or at least you need to have an understanding about superposition, entanglement, these kind of things. We may be able to abstract away from that in the future, but at the moment, I don't see how this could really work out today. And this is, I guess, also one of the large challenges when we talk about in the community about what do we have to accomplish in order to establish quantum computing. Of course, we need physicists who build us the computers, we need the software and so on and so forth. But you know, we also have this huge discussion, you're very familiar with that, on the quantum workforce, right? So we need people trained for this particular community. And right now, my strong feeling is we still need these highly trained experts. So we need to educate people. They have to have a background in quantum computing at some level of abstractions. Maybe in the future, we'll reach a point where we can abstract away from that. But I don't see this more in the midterm or long-term future. Right now, I don't see anyone who is capable of implementing or realizing an application for quantum computing relying solely on conventional classical HDLs, for example. You still need some sort of quantum description means and an understanding of that.
You're a professor at a Austrian university, and I see that in the US, certain universities are starting to offer masters in quantum information science or a PhD program. Could you tell me what the situation is in Europe with regards to educating the workforce on quantum?
It's becoming an issue. So people start bringing that into their lectures and stuff like that. I said I work in quantum computing for 10, 15 years now. And particularly in the master programs, I already had lectures, which I called emerging technologies, where I already sort of covered topics like quantum computing. And because I always felt like, okay, in fact, the young generation who is pursuing their master's or bachelor degrees, maybe their PhD degrees now, they most certainly will be exposed to quantum computing because they have their entire life in front of me. I mean, I kept saying to my students, I am a professor, I've got tenure. I probably could say, well, I don't care anymore because I'm done more or less with my career. I'm just doing it because I still have a passion about it. But you guys, so my students, you still have lots of decades in front of you as computer scientists. You should be aware of what's going on. And I'm doing this already for 10, 15 years. And now also in the universities, programs are built up. I know also in our university, we are putting a focus on that. I mean, literally every European country, probably every country in the world has identified quantum computing is becoming a thing. How established it's going to be, nobody really knows, but people know, okay, people should be educated about it. I'm not saying that we are completely changing our curriculums these days. So we still teach our students these conventional classical programming languages, which of course makes sense because also, as you know, we're not talking about quantum computing is going to replace conventional computing. We're going to have just a more variety of computing paradigms to be used, and quantum computing is one of them. And we are teaching our students how to deal with that. We're beginning to that. So frankly spoken, in my lectures, I cover things like, okay, how to use certain tools like Qiskit, like Circuit, and so on and so forth, and realizing these toy applications and examples they have. But I also have to admit that we're not realizing fully fledged applications yet. But I'm pretty sure in the next years, also my own lectures will change in the sense that we also have not just toy examples we're playing around with, but real world practical relevant examples our students will have to implement on a quantum system. So this is certainly changing, and in universities this is a thing these days, definitely.
And keeping on the European angle, when you look at the big industrial companies in Europe, do they rely on the universities to provide the manpower that they need for the quantum computing exploration projects? Or do they do something else today?
It's a good question. I would say a little bit both of that. Right now, you can really, when I talk to our company partners and when I check out what's happening, and particularly in Europe, I really, and it depends. I see lots of companies who know somehow, okay, I heard about this quantum computing thing. Can you tell me what this is about? So companies who are not really want to make their hands dirty yet, but who feel like, okay, I probably should be informed. Am I missing something? So we have definitely companies like that, which is fine. I mean, I'm not saying everybody should jump on the quantum computing train right now, but when I started 10, 15 years ago, I did this quantum computing thing, and I was the crazy guy with this weird future technologies, which is still far in the future. So I'm already happy that right now we got feedback, particularly from companies who saying, well, this seems to be a thing. Can you teach me? Can you tutor me? Am I missing one? This is one way. And then there are other companies who say, okay, we want to be involved right now. And so you ask the question whether or not this is driven by universities or academia or by industry. I would say, so how I see it, that companies are now also starting using money to fund, for example, universities or research projects, or to fund their own research laboratories within their companies. So I have a little bit feeling that both government and industrial funding on quantum computing significantly have increased, I guess, in an effort to prepare themselves for a time where quantum computing gets established and to be ready for that. So I wouldn't say it's only academia. I also see a lot of companies investing in academia to develop this field. But frankly spoken, in Europe, I'm not aware of any kind of success stories in the sense like, okay, we have a European company who is actually making lots of money with quantum computing, but they're investing, and I'm pretty sure they're investing because they expect maybe in a couple of years some sort of return of investment. So I would say both government and industry is significantly investing in the technology and trying to establish Europe as an important player in the world on this technology.
As we get close to the end of our conversation, let's assume I gave you a magic wand, and now you can control the work plan of the large software and hardware companies and the small ones as well. What do you want them to work on for the next 2 or 3 years in quantum?
It's a good question, because literally, I'm not sure if I should say that publicly, but I have a little the feeling that what the society, the community, industry, governments are currently doing is, to be honest, perfectly in line for what I could wish for. Because as said, I'm sorry that I'm repeating myself, but 10, 15 years ago, I started working on quantum computing, and I was this crazy guy with this future technology. And I had fun, and I really enjoyed that academia is making that possible, that I can work on these emerging technologies. And nowadays, and at that time, I really would love to have this magic wand to sort of convince people that what I'm doing actually has relevance, practical relevance. Right now, I don't see that I need this wand so much, because everyone around, whenever I talk to industry, to governments, or the funding agencies and so on and so forth, I have the feeling that I don't have to convince anyone anymore. And now suddenly that what I've worked in the past 10, 15 years suddenly gains relevance. So maybe if you allow, I would reserve this wand maybe for future days when I really need it again. Right now, I'm just happy that this entire community is developing in a direction where I'm really happy with. Of course, we have to be careful that we are not overreaching it, and there's still lots of challenges. And I mean, people talking about maybe a quantum winter, that the expectations are too high. But right now, I'm really happy with the community is evolving and what's going on, and it's really fun to really see what's popping up. So, no, I said I'm not sure if I should say that publicly, but right now I would say I'm really happy with the developments as they are so far. So maybe let's keep it this way.
So I'm grateful that crazy guys like you have been working on this for 10, 15 years, so that we are where we are today in really what I think is the start of an amazing revolution. Robert, it's been great speaking with you today. Where can people get in touch with you to learn more about your work?
Yeah, so the easiest way is probably just Google my name. Most likely you'll find my webpage. It's www.rwille.de. A little bit complicated, but maybe you can put that in the show notes, or as I said, just Google. Or you can also follow me, if you like, on Twitter, which is my Twitter handle is basically my first and my last name without the vocals, which simply means RBRTWLL. Yeah. And looking forward to hear from anybody who's interested in these kind of topics.
That's perfect. Thanks so much for joining me today.
Thank you very much for having me. It was fun.